Next up, we have Maria Giulia Preti from EPFL in Switzerland, and she's going to be talking to us about extracting eigenmodes directly from the connectome using a framework called graph signal processing.
Thank you. Can you hear me well? Good. So let me put my timer. Perfect. Great, so thanks a lot for being here so numerous today, and also thanks for the organizers for inviting me. I'm very happy to be here today. And so today I will guide you in a very literally educational talk through this framework of graph signal processing. So as Alex said, we will see a similar thing to what James just presented you, so like a harmonic decomposition, structural harmonic decomposition, but specifically the connectome harmonics. But we will also frame it within this mathematical framework of graph signal processing, just to see what is the math and the equation that allows you to basically transfer and translate some of the signal processing concepts to the domain of graphs. So let me start with an outline here. We will first go through the aim. So why do we want to do that? To bridge structure and function. Then, as I said, we will have a pretty theoretical description of this framework, the GSP framework applied to the brain. Then a quite short highlight of where we stand, so how this framework allowed us to investigate the brain so far. And then we'll finish again with a practical. So you also have in the folder a little notebook with the code for GSP. So I'll guide you through that. You can either follow me together, or you can just try to use it later if you want. Okay, so let's start. As we said, the aim of the whole story is to bridge brain structure and function. So more specifically, what we want to do is we want to understand how a structure that is static, and that in our case is given by a structural graph from the tractography, and in particular from the application of a certain brain parcellation to the tractogram that you reconstruct, that allows you to have a brain graph where each node represents a brain region and each edge will represent some quantification of the reconstructed tracts. So how this is static yields a function that is dynamic on top of it. So how basically a function that can come, for example, from fMRI, so the bold signal emerges, dynamic function emerges from the static structure. So for that, as said, we will use graph signal processing. So this framework was just introduced, let's say, quite recently in the application for the brain in the past 5-6 years. And what it allows is actually to translate, as said, typical operations that we know very well from signal processing, like Fourier transform, filtering, to the domain of graphs, basically. So it's a mix between graph theory, if you want, and signal processing. In particular, so what we need is first a graph, so a bunch of nodes, and edges that connect these nodes, and a graph signal. A graph signal is defined as a vector that associates a value to each of the nodes of the graph. So you need obviously the same nodes, so in our case it will be the same parcellation, but just to give you a more intuitive explanation. So the graph could be, if we forget about the brain, for example, the map of the streets or the bus lines, let's say in Brisbane. So each node would be a bus stop, the bus stop location. Each edge that connects to bus stops would be, for example, the bus lines that are running through these two stops. And this would be the graph, okay? So your map, your geographical map with the bus lines. What could be a graph signal? A graph signal, as you can see, it doesn't have edges, so it only has nodes, and it would be a value that you associate to each of the bus stops. For example, it could be the temperature taken at each bus stop, or the presence of ticket machine, or the number of people, the number of persons that are standing at each bus stop at a certain time point. So as you can see, it's just one vector that associates one value for each of the node of your graph. In the case of the brain, so we will consider as graph the structural connectome as said, so brain regions as nodes of a certain parcellation, and structural connections as edges, could be DFA, could be, different metrics, but just conceptually. So yeah, coming from tractography. And the graph signal in this case is a measure of functional activity defined at each time point that assigns you, so with the same parcellation, a level of activity for each brain node. It could be, for example, from the bold time courses. But here, so I also have, just another representation, just so that everyone is in the same page for sure. It's important to notice that, so we have our structural connectome, okay? We have, for example, let's say fMRI time course associated to each node. So here what we consider as signal is not a time course, okay? So a graph signal would be the level of activation, the level of bold at each time point. So if we consider one time point, like the one highlighted here in blue, that would be one graph signal that we consider in the application. So it's one time point, one vector associating one value per brain region, okay? And then what we know about our specific application, because we have time courses recorded, this graph signal will evolve in time, because we will have one value per time points that we acquire, so in our acquisition. Okay, so if you're fine with that, so with the basics of what we consider, then we can dig into the steps of the graph signal processing framework, in particular that we will apply to the brain, so we can call brain GSP framework. So the first step will be finding the connectome basis, right, the modes. So we consider a structural connectome, as said, like the one you see here in the figure, and we decompose it, in particular finding the eigenvectors of the Laplacian of the connectome. So we first need to compute the graph Laplacian. This is the degree matrix minus the adjacency matrix. And then we decompose it, as you see there, in eigenvectors U, each related to an eigenvalue lambda. So the eigenvectors, you can represent them in the brain, as you see. So are these patterns that you see there, because they are of dimensionality of the number of nodes, okay? So this is also what you call structural harmonics, and we will see why you call them harmonics, okay? As you can see, these are patterns going from more global to more localized. We will explain in a second why. So as I said, each of these harmonics is each of these eigenvector U, the brain patterns that you see there, is associated to a value of spatial frequency lambda. So just I wanted to dip in a bit in why do we say that this is a spatial frequency, so where does it come from? It comes from this equation here, the eigen decomposition equation, as you see, with the quadratic equation that defines the value of lambda. And as you can see, lambda is given by, so for each connection, ij, okay, if we basically consider two nodes, I and j in our graph, in our structural graph in this case, the value of lambda is given by the sum, so for each connection, of the square difference between the level of the signal, so the level of the eigenmodes in this case, at the two locations. So if you consider one pattern, for example, let's say U2, you take two nodes and you look at the difference between the signal of these two nodes, so the value in U of these two nodes, okay, and then the square difference, and then multiplied, weighted by the adjacency value in the graph of these two nodes. So how these two nodes were connected, okay, in the structural graph. So as you can notice here, low values of lambda will be present only when basically two nodes that are highly connected, so with a high value of A, also have similar values in the eigenmodes, right? Because then the square difference must be close to 0. Or vice versa, where two nodes that have a different value, because ui and uj will be different, then are not connected in the graph, okay? So they have a low value of A. So this is just to say that basically the level of lambda, so it's called spatial frequency because it's really a measure of spatial total variation in the graph, or in other words, smoothness on the graph. So so this is the plot of lambda. If you order the eigenvalues by increasing lambda, as they are in there. And so you see that low frequency eigenvalues, so when the spatial frequency is closer to 0, will have this shape. So here, that's why we say they're very smooth on the graph. So values that are very connected in the graph will be reflected in values that have similar eigenvector value here. And in fact, you can see that main structural connectivity patterns are captured, like left to right hemisphere. If we go ahead, as we saw before with the harmonics, we will have posterior to anterior, for example. So in other words, you have a lot of information of the structural connectum reflected in these low frequency eigenmodes. On the other hand, if you look at the other end of the spectrum, so the high frequencies, you will find much more localized patterns in which even nodes that are close by, and hypothetically they are strongly connected, they will have very different values. So you have much more this red, blue, that you see there. And the frequency, the spatial frequency, it's higher, okay? You have more variation. Okay, so I took some time because this is really the key of the method, understanding that these modes are different in this sense, so low frequency versus high frequency. Because now the second step would be we take a signal that is a functional activity at one time point, one frame, the one that you see here on the left. And we decompose it as a linear, linear combination of the structural harmonics. So you see here that we have a weighted sum of structural harmonics, and that the estimation of the S hat, that are the spectral coefficients, will give us basically the functional signal at time point t. So one important thing to notice here that is also key for this method is that you see that we allow to estimate or to compute, not to estimate, coefficients that are different at each time point, but the modes do not change. So it's how this method accounts for the fact that modes are static, right? So we have one set of structural eigenmodes, and then we are going to explain different fMRI time points, so the signal at different time points, as a different combinations of these same modes. So this is what varies, so the coefficients. This is also equivalent to graph Fourier transform. So it's called graph Fourier transform in graph signal processing. And we will see now the parallel between the Fourier transform that we have in signal processing and this one. In fact, what you do normally with Fourier transform, you go from the time domain of a signal in time, okay, from a time course, to decompose it in frequencies, in this case in temporal frequencies, right? Because you write it as a linear combination of signals with a different frequency of sinusoids. Here, if you notice, you do exactly the same thing, but we go from the spatial domain of the graph, okay, so our signal in space, to the spectral domain of the graph that is represented by harmonics, the connectum harmonics of different spatial frequencies, okay? So it's the direct translation of the Fourier transform, but in space, basically, in the space of the graph. Yeah, so this is just to reiterate. So we go from the original domain, which is the one of the graph signal, X, into the domain, the spectral domain of the graph, given that is spanned by the eigenvectors, okay, U of the Laplacian. That to do that, it's enough to estimate the X hat coefficients that are the spectral coefficients, the weights that we just estimated. And then once we are in the spectral domain, we can do a bunch of things, right? Like for signal processing. So one example thing that we can do is we can filter our signal simply by multiplying it by a filter mask, H, which, for example, can be an ideal low pass or high pass if you only consider the low pass frequencies or high pass frequencies. And then once we do that in the spectral domain, we can go back to the original domain, so we can reconstruct time courses, we can reconstruct fMRI graph signals that are filtered, so that only includes portions of the original eigenmodes. This is in fact what we do, so it's the third step of the method. So once we decompose our functional signal at one time point into the harmonics, we can then reconstruct it by linear combination of just a portion of the harmonics. For example, we can do a high pass and low pass and just consider low frequency or high frequency eigenmodes. In this case, if we do that, we will obtain two different fMRI signals, one that we can call coupled because it only includes the low frequency eigenmodes that by definition, you remember, they were closer to the structural connectome, so describing better what were the main structural connections, let's say. And one portion that we can call decoupled because it only includes these high frequency patterns that run on top of the main structural connectome. So it always obviously come from the SC, okay? But it's more liberal patterns, let's say, and variable and focused. And you can see there, in fact, from the two reconstructed portions. So here, if you sum them up again, so everything is linear, so you can get back to your original frame. So the result of that if we apply it to every time point, we went from one set of time courses, that is the bolt, okay, to two sets of time courses, one that is more coupled in the sense of aligned to the structure, and one that is more liberal. So it contains this portion of the activity that doesn't, let's say, really depend straightforwardly from the connectome. Then, okay, what we can do, so what we want to do is quantifying the level of structure function coupling at every region, at every node. So one way to do it, we can actually compress out time, and when we have these two time courses, so coupled and decoupled, we can look at the energy of the coupled and decoupled signals. And this is how we get the structural decoupling index, that is a nodal value, so it's a regional measure of structural function coupling that coincides with the ratio between the high pass energy, so the energy in the decoupled time courses computed as the L2 norm of these time courses, and the low pass one, so the coupled one. So this will tell you basically for each region if that region was more consistently coupled or decoupled to the structural connectome during the time of the acquisition. Then another metric that we can compute is, you know, the conventional functional connectivity edge strength. So you have, you see in vertical, you have a fMRI time course at different time points, S1, S2. You can compute Pearson correlation and you get the functional connectome normally. We can do the same, but starting from the two sets of coupled and decoupled time courses. So in that case, we will get two connectomes, functional connectomes, one that is coupled and one that is decoupled version of it. You can, as you can see there, the coupled one looks much more structured and much more similar also to what we know as functional connectome, and the decoupled is really more localized and with patterns that we cannot really recognize better. Okay, so now we have the full pipeline, so we can just make a little summary so that everyone is on board. So the first step was decomposing the structural connectome into structural harmonics. So far everything is structural. We have this new basis of functions of the structural harmonics. Second step is we take the fMRI at one time point and we decompose it into the structural harmonic space, so as a linear combination of structural harmonics. Then in this space, we filter the signal into coupled and decoupled portion, and then we can quantify the level of structure function coupling at the node level or at the edge level, so with the structural decoupling index or with the coupled and decoupled version of the functional connectivity. So yeah, that takes us to the end of the method, so we have a little quiz time. So what are the low frequencies mode encoding? So let's see if my explanation was clear enough. We have A, spatially localized patterns. So these are the low frequencies, okay? So the more coupled. Oops, I spoiled it. But I might trick you, so we don't know. So these are signals that are decoupled from the structure, or signals that are coupled to the structure, or the global signal. So who goes for A? Okay, no one. Who goes for B? Signals that are decoupled. Oh, weirdly, no one. Who goes for C? Okay. And who goes for D? The global signal. Okay, very good. So the most correct answer is definitely C. So these are signals that are coupled to the structure. But indeed, I kind of tricked you because I didn't tell you that maybe multiple answers were correct. So even the global signal, so the global component, so that regards basically all the nodes, will indeed go in the lower frequency because it's the first component that you saw, okay, the DC. I didn't mention it, so it's a good moment to mention it here. And you can decide to remove it or not. I mean, just to know that you will have it there if you don't remove it. Okay, so now, quickly going to the findings. So what did we find out about the brain applying this method? I will really sum up in two slides basically the studies that we did in the past few years, but you can check them out. They're reported references there. So what we have is that we found that during resting state, at the population level, the structure-function coupling looks like that, like a pattern that is not spatially homogeneous, okay? It's not the same at all nodes. But indeed, it's characterized by a gradient, so a spatial variation that goes from regions that are more coupled, that are the ones that you see here in blue, that happen to be the primary sensory regions, to regions that are more decoupled, that instead are regions that are involved in higher cognitive thinking or behaviors. So this spatial pattern, we proved it to be also to have a behavioral relevance. What we showed is also that it is unique to the individual, so you can do very accurately fingerprinting based on that. And really interesting, we also found that in particular, the information that is important for fingerprinting, so to identify uniquely individuals, is in the decoupled portion of the signal. Then you can also successfully do task decoding. So there's not only information about each individual, but also about if you're doing a task or if you're resting and which kind of task. And also we could successfully apply it to different clinical applications where obviously you would need to tweak a bit the settings, as you might need an individual analysis. I forgot to mention as for James, so this whole framework was, based on a structural decomposition of an average connectome. So you have one decomposition for a group if you are working at the group level. That makes it easier, obviously, because you have one decomposition, but in clinical settings you might need to change that, as patients might be different one from the other. That's what we did. Then more recently, what we investigated was also, or what has been found out in literature actually as well, is that structure function signatures also reveal different level of consciousness. This is also what Andrea Lupi, that will talk in the afternoon, investigated in a latest paper. What we saw that goes in line with that is that actually we have specific patterns that characterize different level of drowsiness. In particular, we have a shift towards decoupling only in stages of the resting state, so the first and second half here. So in the first half, where people are normally more alert, and a shift towards coupling, so sort of default state, default mode of the brain in the second part, where people are normally more drowsy. And then recently we also investigated sleep. So here we have data of EEG fMRI, where the time courses are also scored for sleep stages based on EEG, acquired together with the fMRI. And so we can actually classify sleep stages from signatures of coupled and decoupled FC. And to hear more about these results, you can come to my poster, 1392, on again, Friday and Saturday, so the unluck is a lot. But yeah, it's in the afternoon, so you should be fine. Okay, so another little quiz. So structure function coupling measures. They are they are constant throughout the brain. B, they can be indicators of consciousness level. C, they're zero if a person sleeps. And D, they can be used for fingerprinting. Okay, this is easier. So who goes for A? They're constant throughout the brain. Nobody, okay. B, they are indicators of consciousness level. Yes, good. C, they are 0 if a person sleeps. No. And D, they can be used for fingerprinting. Yes, so now you know the trick. Multiple answers are true. So yeah, that's correct. So B and D are true. Okay, so what can we say then to conclude about the strengths and limitations of this framework? So among the strengths, this is a data-driven framework. So you have very few assumptions and parameters that you have to define, and you have no underlying model, which is nice. And yeah, as said, you have this key feature that the same structural patterns can give rise to different functional signals by estimating or by computing different spectral coefficients for each time point. And also it has been proven useful in different settings like clinical, but also fingerprinting, task decoding. So let's say that it's been showing to work, or at least to show us something about the brain that is useful. In terms of limitations, so far we have very little exploration of the temporal dimension. So most of the work that I showed you was based on compressing out time, so static measure of static function, structure function coupling. So a combined space-time analysis would be really interesting to perform, though very complex. But yeah, basically we are in the process also of trying new ways for that. Multimodalities could be explored, like you can have different features at the level of the function and at the level of the structure. And then also we would like to further investigate clinical applications that might be really crucial, let's say, so for which it might be really crucial to investigate structure function together instead of doing that separate for the two components. Okay, so this takes us to the end, to the practical. So I will switch my screen and perfect. I will show you very quickly because it's pretty simple from the code point of view, and I think going through the code might be also very helpful for you to realize what are the operations behind. So here I have in the folder that you have, I just uploaded some data sets of the HCP. So one is a structural connectome that we call A, okay, adjacency matrix, and one is a set of time courses, X, with a Glasser parcellation of 360 regions. And okay, so just the first bit would visualize the data just to see how it looks like. So A is a connectome, region by region, okay? Looks like that. And these are the functional time courses of one subject, so 360 regions and 1200 time points. Then this is also the functional connectome, just for visualization, let's say, purposes. Okay, so this then is the core of the method. As you can see, it's very short. So first, you compute the normalized adjacency matrix. I mean, you can have different type of normalization. What I always went with was a symmetric normalization. So it's you do it by normalizing by the degree matrix D. And then you can compute the normalized Laplacian. Laplacian is D minus A. So if you are in the normalized case, then it becomes the identity minus the normalized A. It's just simplified, the formula, okay? And then here you eigendecompose the Laplacian into the lambdas, so the eigenvalues and eigenvectors U. So as said, you will have a number of eigenvectors, as said before by James, that equals the number of nodes that you have in your decomposition, so in this case 360. Then we sort the eigenvectors by increasing eigenvalues, okay? And here you can see how it looks like. So this is the plot of Laplacian eigenvalues. It's the same that you saw in the presentation. So if you sort them, the first will be 0. That corresponds to the DC component, so the global signal. And then the other ones will be increasing. So if you have a nice spectrum, let's say here, you will see nicely increasing lambdas and not something that goes up very fast and then stays flat, because otherwise you wouldn't have nice differentiation between the eigenmodes. This is just a representation of the Laplacian eigenvector. So this is the eigenvectors matrix. So each column is an eigenmode. You can still visually see that the first columns that correspond to low frequency eigenmodes are more full, let's say, and then these are more sparse, like these are the high frequency modes, you see. It's nice to see it. And then here, what you do is the graph Fourier transform. So you compute the spectral coefficients, x hat, simply with this formula. So by applying the U matrix to your original data. And these are the spectral coefficients that you obtain for each of the signal at each time point, okay? So even here, you see that the first ones, so as said, you get 360 spectral coefficient, the same as the number of harmonics, obviously. So these are the weights that you're gonna use, right? And you can see that the first one are much more used. You see higher values for the first components than the lower one, and that's what we expect. This is just to look at the energy under the, as I said now, the energy of each component in the signal to compute the cutoff, but the cutoff is also up to you. You can use different methods to do it. And then basically what we want to do, as said, is defining two filtering masks, right? So we will have to select for the low pass, only the low pass eigenmodes, and for the high pass, the opposite. So here we define two masks. One defined a certain cutoff, where we only keep the low frequencies and the rest is zero, and another mask where we keep everything else, okay? And the low frequencies are zero. And here we simply apply these masks to the reconstruction so that we obtain two portions of the signal, coupled and decoupled, that are the filtered versions. And for your visualization, they look like this. So these are the two sets of time courses. You remember the ones we saw for subject 1. This would be the coupled signals, and this would be the decoupled signals. So even here you can see that you have much more energy in the coupled than the decoupled. But what we showed is that you have important information as well in the decoupled. And then last, we compute the SDI, okay, as the norm, L2 norm here of the coupled versus decoupled. It's a ratio. It plots like that if you plot it just not on the brain, but if you look at it, in its distribution. And the coupled and decoupled functional connectivity matrices, as you see, the simple Pearson correlation between coupled and decoupled time courses. So same that we saw in the presentation. That's it. So thanks a lot for your attention, and I can help you with the code later, as said, in the breaks if you need, and I'm happy to take your questions.
Thanks very much for a fantastic introduction. Open up for questions, and please, anyone who doesn't want to come up, please post them in the app.
Yeah, thank you very much again for the nice talk. How would you need to adapt this approach for sine graphs where you have positive and negative edges?
Yes, I mean, you mean we do have positive and negative in the signal. You mean in the graph?
For the graph.
Yes, for the functional. Yeah, that is tricky because you don't have real eigenvectors, right? So I mean, that's the reason why. Still, I mean, I never done that. When I did it, I tried to do it with functional connectivity. Well, that is kind of easy because the negative correlations are not that much at the population level for sure. So they kind of get excluded. So you can still only consider the positive, but I don't have a solution for the case in which you have both. Yeah.
Okay. Thank you.
Hi, great talk. I was curious if, just like in the talk before, if this kind of methodology also has a potential kind of local bias. You applied the eigendecomposition to the structural data, and then you applied that eigendecomposition to the functional space to reconstruct stuff. But I'm wondering if maybe that is prioritizing functional connections that have that structural connection as opposed to maybe and therefore are probably localized as many structural connections are, as we were just kind of discussing how the further a connection is, it dissipates the signal. but in some brain networks, we actually do have like kind of longer dependency. So I'm curious if there is that kind of local bias based on the structural decomposition being applied to functional, and then why not kind of apply that decomposition to the functional space directly?
Yeah, as said, thanks a lot for the question. So, I mean, if you apply the decomposition to the function directly, you have functional harmonics that were also explored in literature. I mean, that is also different aim, but also you would encounter this problem of decomposition as said in the first question. To answer your question, I think it all boils down to how you construct, and I mean, your starting point, so the structural connectome, right? So if these long-range connections are well represented in the structural connectome that you reconstruct, then they will still appear as a coupled portion of the signal, right? Because they will be kind of recognized and picked up. So I think your problem is present in case you are, for example, thresholding or using like some processing of the structural connectome that actually ignores this long-range connectivity. And then obviously if they're not there, then the functional portion of the signal that would be derived by that would go in the decoupled. But I think you need to be very accurate indeed, very, very careful with your starting. I mean, that's really like the sanity checks on the connectome is like essential, yeah.
Thank you.
Thanks for a great talk. I just have a question about like doing the same thing on the vertex level. So obviously like the computational issue might be there, but like we have a cluster which can handle 30K or 60K matrices and can do the decomposition. Will there be other like caveats you should be careful about if you wanted to do the same analysis at the vertex level, apart from the computational
Yeah,
issue?
not that I have in mind, meaning that you would simply also look at the surface fMRI instead of the volumes, and you would do all your processing at the surface level. So I didn't do that, but I think in principle it should work apart from the computational, yeah.
Thanks.
We have some online questions. I might just, I see a lot of people kind of standing and struggling to get in. There are some seats, so if you're happy to kind of just move in and grab a seat, ask people to make room. And I should also point out that, you know, earlier I flashed a QR code with a link to the Google Drive with the resources. There's a README file in there that orients you to how to structure and organize that with links to other toolboxes and resources and online manuals and so on. I assume coupled and decoupled are present simultaneously. How do they relate to each other?
Yes, indeed, and it's great that with this method you can actually disentangle these two portions of the signal, so you don't have to decide at each time point if the brain or if a certain region is coupled or decoupled. How they relate to each other? So for me, like at each time point you would have a portion of the signal that really follows the structure, right, the anatomy, so it comes straight forward from that, and a portion that is more liberal, so probably explained by indirected paths of connectivity. I mean, this would be the explanation, basically. And what we found is indeed that certain regions work more on the coupled level and certain on the decoupled. So basically regions that are also proven to be faster in neural transmissions, like the primary sensory ones. Probably they have a higher temporal constraint. They are more often coupled, but this doesn't mean that they do not have a decoupled portion of the signal. And on the other hand, regions that are more higher in cognitive tasks and levels, where you might not have this high temporal constraint, then work more on a long range and I guess also in directed paths of connectivity. That would be my interpretation.
Time for one more question.
Okay, great talk, thanks. I have a question about how do you differentiate variance from idiosyncratic structural morphology directly correlated with spatial frequency from the ones from functional signal?
So for now, I mean, yeah, we have also correlation. It's true with the morphometric features indeed. I mean, for now, we didn't take it into account. I guess you can, yeah, as I said, like in terms of future developments, you could indeed include multiple metrics, or even at the structural level, so morphometry, geometry, and so on, and yeah, somehow account for them. But for now, they are in there, yes.
Thanks.
Well, thanks very much, Giulia.
Thank you.